All right, everyone. In this video, I want to talk to you a little bit about what the roots of a polynomial function are, and also play a little bit with maybe our first example. So I guess we'll call this first bit a definition. The roots of a polynomial function p of x are the solutions to the equation p of x equals 0. Okay? On a graph, we'll be looking a lot at graphs when we're talking about polynomial functions. The roots show up as x-intercepts. If you think about this a little bit, it makes sense, right? So when we write something like this, p of x equals 0, we are literally saying, okay, we know the output is 0. What's the input that makes the output 0? And then, of course, outputs show up as y-coordinates. So if you're thinking about this graphically, you're looking at all of the values of x where the y-coordinate is 0. Oh, well, if the y-coordinate is 0, then it's a point on the x-axis, which is why on a graph the roots show up as x-intercepts. What I want to do next is I want to look at a couple of examples where we not only play around with the idea of roots, but also kind of exploring the idea of degree some more. So for these examples, these polynomials will be written in factored form. Now, this is a luxury that we're going to have to give up pretty soon, but we'll look at one example to start. So say that I had x plus 1 times x minus 2 times 2x minus 5. Okay? So, well, let's talk about the roots. Okay, so we're going to set p of x equal to 0. And then we remember, oh, when you set this product to 0, in order for the product to be 0, the factors have to be 0 one by one. So either x plus 1 is equal to 0, or x minus 2 is equal to 0, or 2x minus 5 is equal to 0. So I'm going to write that out. So if x plus 1 is equal to 0, then x is negative 1. If x minus 2 is equal to 0, then x is 2. And if 2x minus 5 is equal to 0, then x is 5 halves. So these are my roots. I'm going to kind of make them clear. Negative 1, 2, and 5 halves. So there are 3 of them. Now, let's talk a second about the degree of this polynomial. So there's lots of ways to talk about it, and I'm going to use sort of an intuitive approach. So imagine yourself multiplying this out. So I'm going to write here, if we multiplied this out, so let's say if we multiplied p of x out, what's the highest power of x that we will get? Well, let's think about where that highest power of x is going to come from, right? So imagine yourself kind of walking through this multiplication. What are you going to be doing? You're going to be multiplying x's by each other and then by constants, right? So like, for instance, you could multiply x first by 2 or negative 2, and then once you've done that, you could multiply that by 2x. So you're going to be multiplying combinations of x terms and constant terms. But to get the highest power of x, you want to just multiply all of the x terms together. So the highest power of x is going to come from x times 2x, which is 2x cubed. So what we see here is that the highest power of x is 3, so the degree is 3. For now, this might seem like kind of a cute coincidence, but notice the degree was 3 and the number of roots is 3. There are 3 roots in a degree 3 polynomial. Well, maybe this is an accident. So let's look at another example. So say we have 2x minus 1 times x plus 7 times 3x minus 1 times x minus 5. And I'm going to jump straight to the degree this time. Well, again, if you're thinking about how would you end up with the highest power of x, you're going to do this by multiplying all the x terms together. So you'll do 2x times 3x times x. Oh, there's 4 x terms because there are 4 factors. So the degree is 4. Another way that you could think of this is, and this sort of takes us back to properties of exponents if you think about it, but since we know that when we multiply powers, they add, all you need to do to determine the degree of a polynomial written in factored form is look at the degree of the factors and add them all up. So case in point, this is a degree 1 factor, this is a degree 1 factor, this is a degree 1 factor, and this is a degree 1 factor. So since we have 4 degree 1 factors, the degree of the whole product is going to be 1 plus 1 plus 1 plus 1, which is 4. So there's more than one way of thinking about this. All right, so now let's think about the roots. Well, again, we have this luxurious situation where it's written for us in pre-factored form. So we already know that if a product is equal to 0, then we just set the factors to 0 one by one. So, okay, here goes. 2x minus 1 is 0. Okay, so x is a half. X plus 7 is 0. So x is negative 7. 3x minus 1 is 0. So x is 1/3. And then x minus 5 is 0. So x is 5. Okay, well, so there are my roots. 1/2, negative 7, 1/3, and 5. So again, we see that we have 4 roots and a degree 4 polynomial. So I'm going to write up to finish this example, to finish this lesson. This is a huge deal. In fact, it is so huge that it's actually called the fundamental theorem of algebra. A polynomial function of degree n has n roots. So what I just promised you, and I will deliver on this promise, even though it'll take me some machinery to get there, is that if you have a polynomial, the number of roots it has is the same as its degree. So if you have a degree 14 polynomial, it has 14 roots. If you have a degree 9 polynomial, it has 9 roots. Not 9 or fewer, not at least 9, exactly 9. So we're going to continue coming back to this, but I hope that what this lesson shows you, in addition to defining the term roots for us, is that the degree of a polynomial is an incredibly important piece of it. All right, see you all in the next lesson. Bye.